Welcome to today's Maths Club talk. Today with us is Amit Kumar Basistha. He's a PhD student in ISI Bangalore. His interests are in number theory and he's going to give a talk about homological methods in number theory. Over to Amit.
Welcome everyone. Today I'm going to talk about some homological methods that gets used in number theory. Yesterday's talk we saw some homological algebra and how you can take and derive functors and stuff like that. So I'm gonna assume on the contents of yesterday's talk and also some abstract algebra, knowledge of abstract algebra and topology will be helpful towards the end. So let me start with the setup. So we have a group C and an abelian group A. Now I want to define an action of G on it. So what the action should satisfy is one should send A to A. It should respect the group operation on A. And these are pretty natural to assume. So this defines a group action on A. Now under this group action we can make A into a ZG module. So ZG is the grouping of our integer. We can make it into a ZG module just by this is finite sum. They are quite natural. So we will call A. Now, let me introduce some notions. Now, look at this. Yeah, so what I mean by A0 is I have a Z module A. A0 is just, as I said, A0 is same as A. But we are forgetting the Z module structure on it. So we are just considering A0 as an abelian group with the same underlying axis. Now we can define a Z module structure here just by sending here is an obvious map, projection map. As tensor A goes to alpha. And this is projection because one tensor A will go to one dot A. Now look at the kernel of this. Phi kernel of phi. If kernel of phi is a direct summand, we call A equal. So this is same as saying A is a direct summand because what you have is because this is subjective by first reciprocity theorem. And also from here you will have another way of stating the same thing is A itself is a direct summand of lambda tensor, or A is isomorphic to the direct summand of lambda tensor. Similarly, you can define the notion of weakly intersecting. In this case, we consider Hom. And there is a C module structure here by just by sending S dot F of B So in this case, there is an injection from A to form Z lambda comma A, and the injection is given by A goes to phi A, where phi A is the map which in Z to Z1, and this is injective because phi A of 1 is A. So phi A and phi B will differ at A at least. So there will be this thing. Now in this case, A will be called weakly injective if the image is a direct summand of form. And yeah, that is also same as saying that A is direct summand of, because it is injective, it will be isomorphic to the image. So the A is itself isomorphic to some direct summand of. So why we care about this is essentially this will turn out, so weakly projective and weakly injective modules will turn out to be homologically and cohomologically trivial, and that will help us in, certain arguments which is called dimension. So I'll talk about it later. Now, yesterday we saw given a projective resolution of a module, we can get the homology and cohomology. So we can get the homology first, and if you are applying a contravariant function, you can also get the cohomology because the error will be. So in the G module case, we can not only give a projective resolution, we can give a pre-resolution, and we can give a particular pre-resolution. And because we know how the pre-resolution looks like, computing some of the cohomology groups becomes very easy. So, Li, the Z span of element groups. So, this belongs to Z. So, all I+1 tuples of group elements, and you take their linear combinations with Z as well. I define this delta map from Li to Li minus 1, delta of C0, C1, Ci. What Gz hat means, Gz hat is not included in this table. So suppose C0, C1. So suppose it is C2 hat, then it just means C0, C1, C3, C4 and so on. So it is a tuple of I elements, and it is there. Well, and delta square is 0. That is easy to check because if you have I less than k, then first you suppose j less than k. First, when you remove j, you will have -1 for j coming. Now when you remove k, before k there are k minus 1 elements because j has already been removed. So you will have -1 for k minus 1. So you will have 4. But if you do it the other way around, when you remove k, you will have -1 for k coming out. When you remove j, there will be -1 for j coming out because the number of elements in front of j is the same. So the coefficients of the term that doesn't have j and k has different values, so they will cancel out. So you have delta square equal to 3. And in fact, you can also show that this is free. That is a bit messy calculation. You have the explicit form of the map. You have to just write things down and see what's happening. But yeah, it is not difficult to show that this resolution is a free resolution. This resolution is exact. And yeah, I have to leave the map. Yeah, this is a resolution of j. So we'll have it like this. L1, L0, Z. So I have to leave this map. So the map from L0 to Z is just same every element, and this is subjective because end of G will get mapped. So this is a free resolution of Z. two homology groups. Once you have the free resolution, you apply this function. This is a contravariant function. So here because it's a function, it will also send this delta maps to some map between them, and that is actually given by post composition because this is form and form in the first coordinate, so it will be given by post composition. So f will go to f composition because delta makes n not to z, so then we can apply. This is the basic setup. Now, once you have this, you can define the cohomology groups. It is denoted as this. Yesterday we talked about this x and log. So it is defined as the x. Now, two things that I am going to do. Zero homology. So these are the two things that will be needing over and over. The description of the zero homology group, and sometimes I don't know if I'm using it here, but it's always good to get a description of the first homology group. This essentially explains like how helpful it is having an explicit description of the resolution, because you are not giving in terms of some arbitrary projective resolution that you have shown. You already have a form of the resolution at delta maps. So you can calculate these homology groups. Even the second homology groups is not difficult to get, but like it's more computational and less intuitive. This AZ, what is AZ? AZ is just a set of elements of it which are fixed by it. And then the first homology, I was actually gonna compute this homology group, but I don't think for given the amount of time we have, I can go to the computation. It is there in the notes which we are uploading the website, so you can go through them if you want. But these are maps from G to A which satisfy this. These are called cross modes. And if it happens that the action of Z on V is trivial, that is Z dot A is equal to A or if it is trivial action, this is same as under trivial action. This is same as, because in that case this will be modulo the, so this is modulo elements of this S belongs to, this is the kernel by image, right? This is the image, this is the kernel, this is the image. But the thing is, when the action is trivial, this is a 0. Because S dot A is 0, S dot A is A minus A is. So when the action is trivial, this thing vanishes. And this thing becomes just a homomorph. So this is a set of group homomorphism. I will try to not erase that code because we will be needing that. One quick theorem. If A is weakly injective, then it is so all the cohomology groups finishes. The proof is not very long. First of all, note that we can assume A is of this form. Why? Remember yesterday Sankha talked about additive functors, and he mentioned that homology and cohomology are additive functors. So what does that mean is, if you have, it preserves directions. Now, A directs some B is of the form Z, lambda, lambda x. If you take x cube here, this is split up, and if this is 0, this thing automatically has to be. So, it is sufficient to assume A itself is of this group. So, A is of this form. So, I need to compute these groups. So, yeah, this one. By the way, this is. Now, form is right adjacent to the tensor. Okay. So, cohomology of these groups are same as cohomology of these groups. So if you take each group, now in that case, because we had lambda here, it was x cube with respect to lambda. Now this should be x cube with respect to z comma. Now z over itself is a free model. So yesterday, remember, Sankha told that there is no matter what projective resolution you choose, the cohomology group doesn't matter. But it is free of choice. So instead of choosing the free resolution, you can choose this. This is the projective resolution. And everywhere else, because there is such a projective Z. Now when you do this, you compute the cohomology groups, it will be 0. Because this is true in general for any projective model. If you get if you do the projective resolution of projective model and take homology, it will be trivial. So this shows that for weakly injective modules, it is cohomology. Now homology, I'm not going to talk a lot about homology because it will follow analogously. Instead of hom, you will take tensor. So you have this. Say 0. Now, when you take tensor, this direction doesn't flip. When you took hom, the direction flip. Taking tensor, the direction doesn't flip. And you calculate the torque groups. That are the homology. There I will write the zeroth part of homology groups. Wait, I don't need the first one. I'll write the zeroth one. It is denoted by A subscript Z. And it is actually A by BA, where BA is all the elements will become where S runs to Z and A runs to. And these are things that are not difficult to check. You have to just go through the computation properly, and then you will be done. Okay, and yeah, analogously you can prove that if A is weakly projective, then it is homological algebra. The proof will be analogous. You have to just use this time tensor and hom. The other way. Yeah, the other part of the algebra. Now I come to what is called change of group. So, what the basic idea is, suppose you have a map from C prime to C, and you have a C module A. You want, and you have a C prime module A prime, and you have map between A and A prime. You want to give a map between the cohomology. So we will proceed to do that. So consider a C module. A can be given as Z prime module structure. How? F of S prime acting on A is just F of S prime. Now, this makes it a Z module structure. Now, notice this. Also to distinguish between the Z module and Z prime module, I will call this the Z prime module. S sets F star A and A are the same. I am just to distinguish between the two module actions. I am calling A the Z module and F star A the Z prime. There is nothing difference in the level of things. They are the same things. Just to for notational convenience, so that people don't get confused. Why is this true? These are the elements of A fixed by entirety of Z. These are the elements of A fixed by Z prime. Now, Z prime, how does it act? It acts to the elements of Z. So, because F of S prime is an element of Z, anything that is fixed by Z will be fixed by Z prime. Because the action is true, like you go from Z prime to Z and then act with the image. The image is in Z. If every element of Z fixes A, then it will fix the same element. So this is continuous. Now what is this? Like inclusion. Now, here we will use something crucial fact about the cohomological data. So, when when you have a exact sequence between complexes, you get an exact sequence between cohomology. Long exact sequence is cohomology. And it is delta this delta map has some special properties. One of them being, it is a universal delta vector. So what does universal delta vector means is essentially, I'm not going to give the complete rigorous definition. I'm just going to give what is needed for me. Essentially, if you have maps between the zero homology group, you can extend it to a map between the higher cohomology groups. So, to define maps between cohomology groups, it's enough to define between the zero cohomology. This will, in a natural way, because it is a zero delta vector, universal delta vector, it will extend in a natural way to the higher cohomology. So, you get maps from here. Now, consider another module. GBA map. So A prime is some other, say G prime module, and there is a map between A and A prime, such that G is a module map. So what will it do is it will this is an additive map as of now which satisfies this property. So if you act on A by Z prime, this is the action on A by Z prime. It is same as taking the value under Z. This is quite necessary because this is the Z prime action on A and this is the Z prime action on A prime. It is just saying that this map respect the bottom. Now, so essentially it is a module map from F star A to A. Now, since cohomology is a functor, you will get a map from. This is very functorial because it will send object to object and match to match between objects. You compose these two maps and you get a map. So, given a map from Z prime to Z and a nice enough map from A to A prime, the crux of all of this is you can get a map between the cohomology. Now we are going to restrict our attention to some special instances of this. So you take a subgroup H. You take the identity map on A. You will get a map to the H cube Z A to H cube B Z, and this is called restriction. You take H normally 3. You get projection from Z to Z mod X, and you look at the so these are the elements fixed by H, and since H fixes AH, Z mod H will act on it because each of the cosets, so you can just make AH act on it because H acts trivially on H. These are the elements fixed by H. So here you will get a map. This is called the relation. And similarly in homology, if you do everything in homology, in that case you will just get maps in reverse direction. And that is, although that is not enough with justification, I mean it should make sense because you are working the categorical way. So what Hom did is it reversed the arrows. Tensor is not reversing any arrows. So yeah, you just do all the construction and all the properties. You go through everything, and what you will at the end you will end up to map in the reverse direction. So same thing works for cohomology, because I will just be giving the construction for cohomology. The homology construction will go through analogous, because like one is just in the categorical way. So in this case you get, I'll just write the restriction. I mean it is called co-restriction in this case for obvious. You will get map in the other one. Now, I have maps. Before I say that, I should be on. I will not be proving it. The proof is by induction. I won't be using it in this talk either, but I mean it is something that is getting used in the proofs of some of the results that I am getting. So it is important, but for our talk it won't be very important. So if this happens, then come forward these things. Here you apply inflation, you get and here you apply restriction. It's a really nice property. Like particularly in the case, like in many cases what happens is the first homology group vanishes. Like yeah, it happens in many cases. Like even in the field theory case, there is something called Hilbert theorem 90, which says that the Galois group acting on the field extension, the first homology group vanishes. That is the theorem. And from there it will follow that this is also for second group. And second homology group turns out to be very important in number. But I mean that is just something to, I mean I will not be proving it or using it anymore. I'm just letting it just because it's nice. But here, in terms of in cohomology, we got a map from the cohomology group with respect to C to the cohomology group with respect to X. So the natural question to ask is, can I get a map in the other direction? So that I will call as co-restriction, and here can I get a map in the other direction, which I will call as restriction. So restriction is the map from Z to X. So in the other direction Z to X, the map will be called restriction. Is co-restriction. So if you get a map from here to here, it is called co-restriction. Now it is possible, but you have to. I mean that is something, a standard trick in algebra that we will be using, which is called averaging trick. People who have done differential theories will be saying. I mean, I don't think you can differential theories, but like it is quite standard. Like it's a very standard method when you have things which are finite. So if H is a subgroup of finite integers, so you want map from HQ HA to HQ CA. Because of universality of delta functor, we just need a map from the zeroth cohomology. What is the zeroth cohomology group? AH. We want a map to AZ. So I will be doing that. So note that when you have AH, the cosets act on it because H fixes H. So I will give this map norm. This is called a norm map. What you do is you pick representatives S1, S2. Also this need not be a normal subgroup. Although see I can always take the cosets even if it is not a normal subgroup. Normal subgroup just give me the group structure. Here I am nowhere using the group structure, so I can still take the cosets, take their representatives. This is completely valid. So pick representatives of cosets of H in V and define to be I equal 1 to n SI. Now I have to check that I don't have to check definitions or anything. I have to just check that the range is A. Range is obviously A. I have to check the range is containing A. Now for that I have to check just action on G. It is invariant under action on G. Now ZSI. ZSI is in some coset. So it will be some Sj times H. Z of Si will be some Sj times H. So and A is in H, fixed by H. Sj of. And the thing is, two different elements can't go to the same coset because you can cancel out Z always. This is the good thing of having a group. You can always cancel stuff. So this is everything is reciprocal. So this gives a map from H to HC. So you have a map from the zeroth cohomology group to the zeroth cohomology group. So you get map between all the two. C over H finite index. Then you get map from this is called co-restriction. And you get map. In particular, note that when H is when Z is a finite group, So in particular, note that when Z is a finite group, any subgroup works. So when Z is a finite group, you have always this maps. And the notion of finite group is very very useful. What take notice is, say you look at this. So you have this weekly injective, weekly projective stuff. What is that? They are the same when it comes to finite groups. How? Say suppose you have finite group. What is this? This is a Z. ZG, right? ZG is direct sum of Z and Z. Z becomes. So it is direct sum I equal to 1 to n Z dot Zi. Answer. Which is the direct sum comes up. The answer is direct sum from it. I think in the theory class, in the additional classes, this was proved. I don't remember exactly, but yeah, this is not difficult to prove actually. Anyone who knows tensor product should be able to prove this. And here direct sum comes out as direct product. This is a property of form, so Coleridge comes out as inverse. That's basically you can see that this is a contravariant, so the arrows will be reversed. So when it comes out, if it is in the co-category, it will come in the. But the good thing is when you have finite groups, this same as the direction. And it is easy to give isomorphism between this. For every element here, you will have something. You can always give an isomorphism. So what take notice is these things are very fundamental in our in the notions of cohomology and homology. Coincides in the case of finite groups. So what he wanted to see was there a deeper connection. So essentially, when you have an exact sequence. So essentially, what we are going to do is when you have an exact sequence, you have this. And so on. It increases. It increases. And the homology groups, they go in decreasing fashion. So it ends on the right, it goes up to infinity on the left. Here it ends on the left, goes up to infinity on the left. So is there a way to somehow modify this group and this group so that I can patch up the two sequences? So it is just infinite of both of these. So there is one. So these are called the 8 cohomology groups, and they have both the homology groups on the right, cohomology groups on the left, homology groups on the left, and for every exact sequence you get a infinite sequence, extending on both directions. So I'm going to define that. This is just for here also I define a norm. Norm is an element of say Z, which is defined by, Z is finite. Z is finite. This is the same norm map that we gave here with H considered to be the trivial. So these are finite sum because these are finite. And norm defines a map from A to A divided by A equals to. Now let's look at the kernel and image. For notational sake, I will written IC to be the ideal generated by MH of the form in Z. Now note that IC is in the kernel of IC times A belongs to kernel of subset of kernel. Why? You take anything of this form T minus 1 times A, you apply norm to it, you get summation S belongs to T, S dot T minus 1 dot A. You break up the sum, you get STA minus summation S, but this is just a permutation of the two values. So these two sums are the same. So IC of A is contained in kernel of A. And image of n is contained in A. I mean, this is the same thing that we did for finite integral. Because I mean, essentially you are everything out. So if you multiply by z, it will become z times s, which is the permutation of the group. So it is the same sum. So this is obvious. So this is actually from here. So this induces a map n star from A by ICA to A. Now what is A by ICA? What was dA? dA was s minus 1 dot A. So dA is same as ICA. So this is the zeroth homology, and this is zeroth cohomology. The natural thing to do is take its kernel and co-kernel. So the zeroth kth cohomology group is defined to be co-kernel of n, which is same as Az by Na. Na is just the image of A, and since this map to Az by the image of and the subscript notation. I mean, this is kernel of n, but you are going only to IC. Kernel of n. So, what you have is you have this zero kth cohomology group, and we will see how they give you a long exact sequence in 4 seconds. So, for that, I will let you just consider this. In homology, you have this. It's not difficult to check this diagram is completely. You have to just write everything down and then just check for this square. It's just computation. Because you know you have explained description of this map. You know these are delta functions. You can construct the delta functions using the snake lemma that Sankha Subhra. So I mean this is just messy calculation, but you can always show that this diagram is useful. Now if we do a snake lemma here, you will get this. Kernel of n star. Kernel of n star is hn 0 or hn 0. Kernel of nb star is hn 0 cb to hn 0 cc. Then you have co-kernel of this thing. So co-kernel is zeroth cohomology group. can always continue. So you have a sequence extending in both ways. So I will define the take homology groups. I mean, these are the take homology groups. It is nothing more than this. H set and CA is just H and CA for n bigger than equal to 1. H set and CA is equal to H n minus 1 CA for n less than equal to minus 2. So you are getting the first from the first homology group. Now I have to define H0 and H minus 2. It is just co-kernel of n star. And this is it follows that if you have a short exact sequence, you will get a exact sequence of long exact sequence of take homological extending both ways. And actually what happens is this restriction co-restriction maps extend to all the take homology. So what we saw is it extends to these groups, it extends to these groups. What you can show is it extends for these groups. Like it's the same thing. You just it follows that you can go modulo the quotients, whatever quotients you need to go. Here it will be restricted to this, and in the other case you can just go modulo. So yeah. Yeah, the final thing that I need before going into number theory is topology. So I'm not going to go to the construction of top products. You can find it anywhere like Neukers, Homological Number Theory, or I mean even I think Kenneth Brown should have it, or Cartan-Eisenberg has it. As far as I know, Cartan-Eisenberg and Neukers has it. Brown I have not said. I mean I'll write down the references here. So for every pair of pair PQ of integers, you get a map. And B are G modules. This tensor product over there. So I need a G module structure. So how is this system? It's called a diagonal action. Active diagonal. I'm not going to define what this map is. It is a bit complicated to define. I mean, you define it analogously to a. I mean, you assume that it satisfies certain properties. The properties, when you look at it, it looks like same as the differentiation map. The differentiation of A tensor B is differentiation of A plus then differentiation of B. So it looks analogous to the differentiation map. But yeah, I mean, you have to go through some painful calculations and computations to get this one. And it has some nice properties with respect to this delta function. So what happens when you take delta functions and then apply cup products? Or first take cup products and then apply the functions. So there are some nice properties related to that. I will not be reading it. I will just read the existence of a map from here to here, which is called the cup products, and which behave well with everything that we know. And I'm just gonna give the instant when p equal to q equal to 0. And also, yeah, this is which notation is. And when p equal to q equal to 0, this map is given by just passing on to a question. Because this is just AC, this is BC, and this is integer. Because anything that is fixed by both A and B will be fixed under this. is components. Now I go into the definition of Brouwer group. What is a Brouwer group? So Brouwer group will not be very important. Like you will not see the importance of Brouwer group in this talk, because what I am going to do in this talk is I will abstract out all the number theory in terms of axioms. So that is called abstract classical theory. So you don't go into verifying that the number, that this number field or this field that I want to study verifies this field. You just it is actually general thing in mathematics. You work with real numbers. You realize open sets have the property that arbitrary union is open and finite interaction is open. So when you define topology, you define in terms of arbitrary union and finite intersection. And you get results for topological space. You verify that it happens for real numbers, because in real numbers the open sets. So sometimes you realize that certain properties are more important in the object itself. So you want to axiomatize those things and then work assuming those things. So I will give motivation where those axioms are coming from. I am not going to go through the verifications. I mean, that is probably one or two more chapters of share to cover if I want to go through the verification. But yeah, but I will at the very least give the motivation why the axioms are coming, or from where the axioms are coming. So Brouwer group. Now here the group and modules will be more specific. What is the group? It is the Galois group of some field. What is the module? It is the bigger group. What is the action? It acts on the element and gives another element of it. So I can define this family. Sometimes it will be just denoted by, yeah, so you can define it on the, so you can consider L over K, L as an additive module and also as a multiplicative module. L as both addition and multiplication, right? So you can consider it in two ways. You can just take the additive field, so additive group of the field, or you can take the multiplicative group. So HQ L over K will denote the multiplicative. So what? So the Brouwer group, I'm just gonna give the definition. I'm not gonna bother. Yeah, there are some other stuff that I have written down. I don't think I'm at the time to do. Yeah. So you take a separable closure of the field. This called a product. So what is the separable closure? It is the all the set of all elements in that algebraic closure which is separable closure. Now, note that this depends on which algebraic closure you are choosing, because algebraic closure is not unique, it is unique up to isomorphism. So, the natural question arises is the Brouwer group unique up to the choice of the algebraic closure? And it turns out it is. So, that is actually can be justified using change of group. So, you are getting match between the two algebraic closures, and then from there you can justify it. I'm not going to go through the calculation. I'll give references and stuff like that. It's also in my notes, so you can have a look at that as well. So yeah, so that's why it is often this thing is omitted because it doesn't depend on the separate closure. So this is called a Brouwer, and this is important in number theory. I think you will be able to see some instances of it, but not everything. Especially while computing the cohomology of what is called a Z-band. This comes up very often. Now I'm going to go to number 2 for this. Now here, we begin with a group, and we begin with collection of subgroups of n. And it satisfies the following property. And F will be, I will denote F by actually product of it. I mean this notation everything comes from Galois. And actually this indexing set E will be called field. So I mean we are not working with Galois group, but this will be called Z is a group, the indexing set, the indexes will be called fields. And I mean this follows from Galois theory actually. If you have fields, so we are just doing a construction analogous to Galois theory. When you have intersection of the Galois group with the Galois group before. For every subgroup prime of Z that contains a subgroup of the form Z of M. So one of these subgroups, then Z itself is of the form Z of M. If S belongs to Z and F belongs to X, then the conjugate is equal to C of F prime for some F prime, and this F prime will be denoted by S. Now I will just call these elements of this indexing set fields. If it happens that Z of T is contained in Z of F, I will write F Z of F. I will write F. Just include the limit. I mean this is just notation. This doesn't have anything to do with together. It's just denoting it in that. And this index will also be called, if ZE is normal in ZF, ZF is normal in ZF, we will call this extension F over D Galois. And this group will be called its Galois. And I think that's it. Yeah, also if this is Galois, then the order of the Galois group will be called as the index of the extension. So now this is not now this gives us condition of the group. We also need a module for the group to act. The conditions of the module is simple. Module, say abelian group, C module, also a C module, and for every A belongs to A, for all A belongs to A, stabilizer of A is equal to some Z. Then this system course, if you take all the Galois extension of a field, all the finite Galois extension of a field, as the subgroups, and you take the maximal Galois extension as the, then you get this is a formation. This is obvious because of the notation that I have. Now, by AE, I will denote A0 Z comma A, which is so the elements of A fixed by Z, I will just denote it by A. And if F over A is Galois, then the Galois group acts on A. Why? Because AF are the elements fixed by Z subscript. So it will be so this quotient group will act on AF, and that will be our main point of study. And this is obvious because the elements that Z fixes are in. Yeah, and also this group, so in general, HQ, Z, F1, we denoted by now. Yeah, I'm gonna give two maps actually. Not two actually. I'll just need one. Yeah, I'll just give one more map. Just like I did this restriction and co-restriction. So this is one of the maps that you obtain by Sankha. So you have an isomorphism. F over E Galois. Then you have an isomorphism from that sends E to STS. And you have a map from this also isomorphism A goes to S. So by change of group, whatever we define that if you have a map between the groups and if you have a map between the modules, you get a map between the cohomology. And in fact, you get map between the plate cohomology. And that is easy to say because you get map between homology, you get map between cohomology, and then in the middle, the two things you have to just check that they are identical. Then you can go modulo something. So restriction, inflation, co-restriction, and this S. These four maps will be important. Now I will define what a glass formation is. Class formation is a formation alongside a map. The from for every Algebra. So is that for all homological Algebra. Why is that? Yeah, I need I have a map. So let me just say what this map is in number theory. So what happens is, when you have in number theory, you have an exact like you have in say A complete with some discrete valuation, and you take its residue field. Residue field is just you have valuation on K. Residue field is just you quotient it out by the how do I say this? Say you have said Px. So you have QP, you have the Px, this is the ring of integers. Here you have the ideal, the maximal ideal. You quotient it out by the maximal ideal. That will give you another field because quotienting by the maximal. Because what you can show is if you have a local field, the ring of integers, which are the elements of elevation becoming 0. So you have some elevation on it, and these are the elements of elevation becoming 0. And it is a local ring. Local ring means it has one maximal ideal. So it has a single maximal ideal. You quotient out by that maximal ideal. Otherwise, in the terms of Px is the group becomes. So in a local field, one of the axioms of local field is the residue field. This field will be called the residue field. The residue field is finite. So you have a field complete under discrete valuation. Then you have this exact. And in terms of in the case of local fields, what happens is this group is not only local, like there is a general something called quasi-finite. So when k bar is quasi-finite, it is 0 and none. As the name suggests, any finite field should be quasi-finite. So when local fields it is local fields, it is the this becomes 0. So what you have is an isomorphism from here to here. And what is this? This is the separable closure. So any Galois extension will be sitting inside this because every Galois extension is separable. So it will be sitting inside the separable closure. So what it does is this is an isomorphism. So this it maps. So this whatever this map is, it maps this subgroup of Bk to the n torsion elements. So n torsion elements is the elements n to the 1. Because these are elements 1 by n, 2 by n, 3 by n up to n minus 1 by n and 0. Yeah, it will map to this. Map injecting because the isomorphism is anyway injecting and this should be on. Where n is the degree of freedom. So essentially we are axiomatizing this. We are saying that for every Galois extension you have such. And the first axiom is the first homological premises. And this is for number theory case whenever we need it is a Silber's theorem like this. Axiom 2. Okay, before saying axiom 2, I should say something. You got this? And this impression from the question. So f prime contains f. You can say just write down what this proves are, and you can say that is the same as this impression. So here is this map. So note that here is a directed indexing set. So f contained in f prime, you have a map from f to f. So you can, so this form a directed system. You can take its direct limit. So this is defined as direct limit of another implicit limit. And what happens is, now I'll just draw the diagram for direct limit. The direct limit, and you have move there. You have maps to here, you have maps to here. By universal property will have a map to there. And in the Algebra theory case, the direct limit is just a ground. Because these are all separable extensions. If you take the direct limit, it becomes the separable closure. So it is a direct limit of separable closure is a direct limit of. I mean the Galois group is the inverse limit. The cohomology groups are there. That is because cohomology is again like Hom takes inverse limits to direct limits. If you take Hom of inverse limit, you will get direct limit. I mean that follows from contravariance and it being ragged. So yeah, so this map will also be denoted as. So it's a bit confusing because in this not specifying which extension you are taking or if you are defining it from the direct limit, but it will be clear from the context. Example is in B is injected. And maps and is the degree of the extension. This is the first. In BF well with restrictions. We have restriction maps because of obvious like we have a subgroup structure on the Galois group and then we have also depending on subgroups. So we have restriction maps. Prime is complete. So the Galois group will be subgroups, so we have restriction maps. This is same as the degree of the restriction times invariant. These are the two axioms. If it satisfies these two axioms, it is called a class term. And here is one theorem that I was going to prove. I don't think I will have time for it. I will just state the theorem. The proof is nice. I mean, it's not very difficult at all. It uses some of the results that I have been talking about. For every extension inclined, so here's 3 parts. It actually shows that this in BFUL with co-restriction and the IBFUL with co-restriction and this S term. For every extension, different money, the homomorphism. So you can keep a, so you have restriction map here. You can just pass on to the limit and you can give a restriction map within the direct limits. And this should follow from the properties of direct limit for those of who are familiar with that. Yes? Subjective. And note that to say that the mathematical direct limit is subjective, you can just say that for the directed system it is subjective because taking derivative is the exact function. So it doesn't matter. property, the homology, restriction will be in the other paragraph. And part 2 will follow from part 1 using some properties of restriction and coercion. The third one is with respect to this we have S star. For all S belongs to G, we have S star. Because it can always pass on the limit in F. And it satisfies. Now, why do we care about this? Essentially, this gives us what is called the reciprocity, and that is very important because reciprocity isomorphism in the local case gives you the Artin reciprocity theorem, and the quadratic reciprocity, cubic reciprocity, all those things actually follow from it. The higher reciprocity laws follows from it. So then this denote the element this belongs to this. The element such that because in maps it injectively to Q mod J, you will have a unique element which maps to 1 by 1. So that unique element will be denoted by U at the only the theorem from it. And proving this theorem is actually highly non-trivial because it uses all the Tate cohomology machinery that I have been using, and also it uses characterization of homologically trivial modules in terms of homological trivial modules in terms of how they behave with the pseudo subgroups of the group and stuff like that. So there are pseudo subgroups comes up. Even in this theorem, pseudo subgroup will come up. CB final A is only, and A belongs to X to Z. And let ZP be some G into pseudo subgroup of Z for all. So every time it collect all these pseudo subgroups. Now suppose the first homological group is trivial, and the second homological group is generated by this. And now note that these two cases are satisfied in the case of transformation. Essentially, those are axiom 1 and axiom 2. Axiom 1 is the first homological group is trivial. Axiom 2, along with this thing, gives you that the restriction, because H to ZP is generated by restriction. Then what does that mean? H to ZP is cyclic. We know that because it has been mapped on injectively. This is an injective map and it maps it onto this. So it is isomorphic to this, which is cyclic. So it is cyclic, and the generator is of the form this thing that can be gotten by using this tool. So these two cases are satisfied in our case of transformation. Essentially, those are the two axioms. Let me call by AZ. You know the restriction. So Z is a subgroup. Z is not a group. Small z is a subgroup. You have the cup product. You can take so AZ is an element of H2. So you can take cup product with AZ. So this is a trivial action on Z. Because here this is just given by this cup product. But you will get something in h n plus 2 z comma z tensor n which is equal to 8. So, and this can be gotten in any case by the cup product. What else says is this homology is an action. And we can apply this to our we can apply this to our case of transformation. In that case, this will be the element AZ. And what you can show is with cup product. So you have a map theta hat n, theta prime, and over here. Now we will just look at a particular example, particularly when n is equal to -1. So what is the right hand side? Right hand side is this is the zero cohomology group. This is just AF by if you look at here the zero cohomology group is zero homology. Zero date cohomology. Date cohomology group was AZ quotiented by it was the quotient of the zero cohomology. So this is the zero cohomology group. This is the date, and it is same as. And HF minus 2 and over the not F. CFE. If I should prove this, but is isomorphic to abelianization of the abelianization means you just take the Galois group and quotient it out by the complexity. And this is not just true for entity, the Galois group for entity. It is always true. If you take H1, I mean, you can take it as an exercise of this. I mean, I have to prove it in my notes, but don't be get it. So if you take this is the same as the abelianization. So what you get is you get a map from the explanation of the development to this question. The inverse of this map is called the reciprocity, and that will be denoted by, so I will not give a map from the question, I will just give a map from A to this, whose kernel will be this, and I mean it is denoted like, I mean this map is explicit enough, you can compute top product. So in cell itself there is a chapter called computation of top product. So in many cases you can compute how the top product looks like. So this map is explicit enough. It's just that, yeah, I mean, not like you can just write it. I mean, it will be an element. It can be defined properly, but the inverse of this map is called the reciprocity. And yeah, there are properties of reciprocity also in terms of its characters and stuff like that. Yeah, I'm not going into that. I'm gonna give some functorial properties of the reciprocity. So, from A prime to A, you can go into the something. From A prime, so F you can go to the elimination of this. From here, you can go to the elimination of this. In here, there is a projection because G E prime is contained in G. So you can project this into here, and then because it is getting projected into the abelian group, you will get mapped into that abelian. And this is not difficult to show that this is just the natural projection that you can take. It is just quotient filling class. Secondly, I have this one. A is contained in A. What this map is, I will just mention now. Is that a reciprocity map? And what is this map? This is called this is a classical map in group theory, which is called a transfer map, and it can be given in terms of homology as well. So we have the restriction map. We have those restriction maps. Yeah, we have this restriction map for finite space. And this is isomorphic to the abelian. This is isomorphic to the abelian. So this map is classically called the transfer map, and this notation comes from the German translation of the word transfer. And the fourth one is the most important thing, because this lets us pass into the inverse limit and give a map from A into the inverse limit. So, I don't know if I should go into it, but yeah, I mean, this allows us to define a map from A. because here you have f prime contains f, but you have the maps from f prime to f. So this is an inverse system, not a radical system. So you have the map of the inverse. The reciprocity map essentially extends to the inverse to and that is defined to be a goes to b, a comma. And this gives you how this map behaves to it as normal. Yeah, now I am going to talk into the final part of my talk. So, I want to study what the kernel of this map is, the reciprocity. So, the kernel is essentially an over of A or some A. So, I want to study the kernels. So, I want some characterization. So, the main crux of the talk will be giving a characterization of these norm groups. So, norm group is a subgroup I of A is a norm group. If there exists an extension B prime or E such that I is equal to I'm going to give some theorems that will have to go through. So, what it says is, say, suppose you have B prime contains E, you will have a maximum abelian extension, which is just, so you have a Galois group, and you take the abelianization of the Galois group, this will be the cosine of the Galois group, that will correspond to some sub-extension here, so you will get a maximal, and that is the largest extension, because any abelian subgroup will be abelian subgroup of the Galois group will be complete. Any other abelian extension will be complete. So, what it says is, to study the norm groups, it is enough to study the abelian extensions. And this is very nice because what happens is, when you want to compute the tail cohomology groups, it is always easy to compute them for cyclic groups. And yeah, it is like when you have to compute tail cohomology groups, cyclic groups, you have to just compute two groups, H0 and H1. Others are equal to them, not only just follows from them, others are equal to them. So the even ones are equal to H0, the odd ones are equal to H1. So, and when you have finite abelian groups, you can always use structure theorem to break it down to product of cyclic components and then you compute tail cohomology from each of the cyclic components. So that's why it's good that there is a characterization in terms of abelian extension. And a corollary of this is And the final theorem is so I will denote by IF on AF. So this is a inclusion reversing one-to-one correspondence between abelian extensions and the norm groups, such that this is what it says is, if you take intersection of two norm groups, you get a norm group, and if you add two norm groups, you also get a norm group. And in any subgroup of A that contains a norm group, is itself a norm group. So from this I got the main result of this law, which is the existence theorem. So existence theorem assumes that you have some topology on this A's. I mean, in case of local fields, you can always give topology to this A's. And once you have the topologies, you can give a topological characterization of the norm. So existence theorem. First, assume A is an inverse topology. The topology is such that it respects the group action and it also respects the group operations. So the addition is continuous and scalar multiplication with the group element is continuous, which is a natural coexistence. And we will assume that if A is contained in A, the topology on A is the same as the subspace topology from A. So the topology agrees with the subspace. This implies that the norm map is continuous, because the norm map is just action of the group and then addition. Group action is continuous, addition is continuous, the norm map is continuous. Axiom 1. I mean, I'm going to axiomatize everything because for every extension I have one in. As compact kernel and closed field. Which is same as saying the local fields case, it is same as saying the matrix structure. Because it will be because these are locally compact and compact. These are local fields. Now one definition. The universal norm group of E is just the intersection of all the norm groups for all. So it will be intersection of I for all I. So this is the universal norm group. And yeah, the first theorem is I'm just gonna there are three theorems, I'm gonna put the last one. The other two are in my notes. One thing I will try to do. The proof is actually nice. We use finite intersection property to construct a sequence of compact sets, and then use that the intersection has to be non-empty. There is nothing. The second axiom is the one which is very tricky, which is the one that is very tricky to verify in practical applications. So for every prime number P, there exists a field in P such that for any E that contains EP, the map P of AP to A to A, which ends A to P dot A, satisfies kernel of phi P is compact and image of phi P contains characteristic. And what are these EP in the number theory situation? If the characteristic of the field is Q, say, EP will be K adjoin the roots of each roots of EP. And if that characteristic is P, then it is just the field fields. So this is the second example, and the theorem shows another theorem shows the group D is divisible. And D is the intersection of n dot D. Yeah, so I go into the final theorem, the existence theorem. And I'm going to prove this theorem. I contained in A is a norm group. Analogy, it is closed end of final. Now necessity is clear because we proved that the norm groups are closed and we proved that the norm groups are of finite. So one direction is already done. The other direction we need to prove that if a group is of closed at a finite index, then it is a norm group. Now note that if a group is closed at a finite index, it is okay. Why? The complement of the group is union of cosets, finitely many cosets, and each of the cosets is closed. So the complement is finite union of cosets. So the group itself, the subgroup itself is open. So it is both open and closed. So suppose AE over N, and note that A is an abelian, so any subgroup is 1. So A over N, suppose it has number of elements N, and I goes which is plus I over N. So, and also instead of AE, I will denote it by A. Just I don't want to write it down. Implies A minus I is closed. Which implies A minus I intersection E. Oh wait. Let me give you a third example. I have not given the third. And what UE turns out in the local fields case is the UE is the group of units of field. So yeah. So we have assumed the existence of a complex subgroup such that every closed subgroup finite index that contains UE is a norm subgroup. Now A modulo I intersection AB is a closed subgroup of a compact group, so it is compact. And n dot A is contained in I. Why? A represented by the group of order n. So every element will have order dividing n. So n dot A will be 3 will be the identity. So n dot A is contained in I. Now note that D is contained in intersection of n dot A. Is equal to intersection, which is contained in n dot A. Which is contained in, and D is equal to intersection of all the norms. So I will by n I will denote n will run over all the norms. Now A minus n is contains A minus I. What is A minus n? It is just union of A minus n containing A minus I. Which contains A minus I intersection. Now n itself is a norm group, so it is closed and a finite index. So A intersection n is open. A complement n is open. So this compact set is covered by open sets. It's an open cover. So we will find a finite subcover. You take everything here and note that intersection of norm groups is a norm. So finite intersection will be a norm. So I can just call it some n prime, where n prime is a norm. This is the set. And then n prime intersection B is contained, because we take cut off this thing and then intersect with B. This thing is 0 here. Now n intersection I is closed because it is intersection of two closed sets. And it is of finite index because intersection of two groups of finite index is also a group of finite index. That is something that you can find in the first course. So this is closed and of finite index, hence it is open. And what you can show is UV is also closed of finite index. So if this is closed of finite index, you can show that this is also closed of finite index. This not difficult. And this contains UV. So by the third axiom, this is a norm group. So n prime intersection UV plus this is the interaction of two norm groups, and this is also norm group. And n prime interaction UV is contained in I, and n prime interaction I is contained in I. So this whole norm group n double prime is contained in I. Now look at this here. Any subgroup of A that contains a norm group is itself a norm group. So I is a subgroup of A that contains a norm group. So I itself is a norm group. So this proves the characterization of norm groups in this situation, that it is a norm group, it cannot be this closure. So this is the end of the talk.
methods of references.
Yeah, so for the group cohomology part, you can look at Sankha Subhra Homological Algebra. Or you can look at group cohomology by Prerequisites. Or there are good notes actually. Notes on homological algebra. Notes by here's notes in both homological algebra and group cohomology. These are notes of UCLA. They have really good notes. For the local fields parts, and Weibull is there obviously. If you want to from there. For the number theory part, the things that are presented here is from the book Local Fields by JP Sen. And also there is a really good book, classical theory. So this abstract classical theory part is here presented there very nicely. By Arting and Tate. And of course there is Neukers and but I think Castles and
Any more questions? Let's thank the speaker once again.